Next, I'm happy to introduce Biddy Razafimahatratra from University of Regina, who's going to talk to us about the Erdo s-Ko-Rado theorem for transitive groups.
Okay, thank you very much. So first and foremost, I'd like to thank the organizers for giving me the opportunity to present my work in this conference. So I'm going to talk about the Erdo s-Ko-Rado theorem for transitive groups. And this is a joint work with Pablo Spiga and my supervisor, Karen Marr. Okay, so first of all, let's talk about the Erdo s-Ko-Rado theorem. So this is a classical theorem in extremal combinatorics. So if F is a family of the ground set N here, and well, we let F be a family like this, and we say that F is intersecting if for any two elements in F, the intersection is not empty. So what Erdo, s-Ko, and Rado proved in 1961 is that when we take n greater or equal to 2k, and F is an intersecting family of k subsets of n, then the size of F is at most n minus 1 choose k minus 1. And they also characterized the families, the maximum intersecting families. So when n is greater or equal to 2k plus 1, then the maximum intersecting families are exactly the families that are called stars. So they consist of the k subsets that contain a fixed element. So this is the classical Erdo s-Ko-Rado theorem, and we can extend this to permutation groups. So first of all, we need to know how permutations intersect. So if F is a subset of the symmetric group, then we say that F is intersecting if any two permutations of F agree on some element of the set N. And so what Deza and Frankel proved for the intersecting family of the symmetric group is the following. So if F is in an intersecting family of the symmetric group, then the size of F is at most n minus 1 factorial. And notice here that this is exactly the size of a point stabilizer in the symmetric group. So this was proved by Deza and Frankel in 1977. And in 2004, Cameron and Ku, Larose and Malvenuto proved that the maximum intersecting families are exactly cosets of point stabilizers of sim n. So the question is, well, the natural question is, can we extend the theorem of Deza and Frankel for subgroups of the symmetric group? So in other words, permutation groups of degree n? And the answer is no, and it depends on the structure of the subgroup, in fact. So let's see this example first. So we take the alternating group on 4 with its natural action on the set 4, and we take the induced action of this group on the two subsets of 4. So there are six two subsets of 4, and then this group G is isomorphic to the subgroup of sim6. And then when you look at the stabilizer of G tilde, it has size 2, but we can actually find an intersecting family that has cardinality larger than 2. So this is why the previous theorem failed for some permutation groups. So we have to consider some definitions. So if you take a finite transitive group G acting on a set omega that has a cardinality n, then the intersection density of an intersecting family is the rational number, which is the cardinality of the family F divided by the size of a point stabilizer, and the intersection density of the transitive group G is the max of these intersection density of the intersecting families. So as a quick observation, so if we take G to be a transitive group, then the intersection density of G is always greater or equal to 1 because G of omega is always an intersecting family of G. Okay, so because the Design-Frankel results fail for some permutation groups, so we consider the following definition. So here we let G be a finite transitive groups, and we require transitivity here because we just want the point of omega to be equivalent under the action of G. And we say that G has the EKR property if the intersection density of G is equal to 1. So here, this corresponds to the size of an intersecting family is at most the size of a point stabilizer. And we say that G has the strict EKR property. When G has the EKR property, first of all, and an intersecting family that has intersection density 1 has to be a coset of a point stabilizer of G. So these are some results in this area. So one of the biggest results in this area is by Mar, Spiga, and Tiep in 2015, which says that when we have a finite two-transitive group, then G has the EKR property. Ellis, Friedgut, and Pilpel proved the following. So when we fix a t in n in the natural number, then for some n large enough, the action of sim n on the t tuples of n has the EKR property. And in 2012, Ellis proved the analog of this result of Ellis, Friedgut, and Pilpel for the action of the symmetric group on the T subsets. So both of these last two results are asymptotic results. Okay, so what is the goal of my of this project of mine? So the goal is to classify the finite transitive groups that have the EKR property, but I think this is in fact very difficult, and I think the strict EKR property is even more difficult. So let's now talk about some of the tools that we need to study the EKR property of transitive groups. And the classical tool is the derangement graph of a transitive group. So we let G again be a finite transitive group acting on omega, and der of G is the set of all derangements of G. So that is the permutations without fixed points. So we define the derangement graph of G to be the Cayley graph of G, and with connection set equal to the set of derangement of G. So in other words, it's the graph that has vertex set G, and two group elements, G and H, are adjacent if HG inverse or GH inverse is a derangement. So as a quick example, if you look at the symmetric group on 3 with its natural action, so this is the derangement graph. So you can see here that the identity is adjacent to the guys in the connection set. So the 3 cycles, and here the product of any 2 transposition will be a 3 cycles, so they are adjacent as well. And so why are we interested in these kind of graphs? So we have the following equivalence. So if F is an intersecting family of G, then F is a co-clique or maybe an independent set. Independent set is more used in graph theory. So F is a co-clique of the derangement graph. And this is because of how we defined the edges of the derangement graph. So now studying the EKR property of a transitive group becomes equivalent to finding the size of the max co-clicks in the derangement graph. So this is another example of a derangement graph, and this is exactly the derangement graph of the example that we saw earlier, so the alternating group on 6. And you can see here that the green vertices here, they all have fixed point, and the red and the blue vertices, they are all product of 3 cycles, so they are derangements since the group has degree 6 here. And this graph is in fact a complete tripartite graph. And this is in fact a natural example of a transitive group that doesn't have the EKR property. So now I'm going to talk about transitive groups that do not have the EKR property. And so the transitive groups whose derangement graphs are complete multipartite graphs are the most natural example of such groups. So imagine this is our derangement graph. It is a complete multipartite graph. So this is the identity, and we have a permutation here. So these 2 vertices are adjacent. So that means these vertices G, this vertex G here is a derangement. And in fact, anything that is adjacent to the identity is a derangement. So all of the parts that do not contain the identity, they all consist of derangement. And if we have a permutation G prime that fixes a point, then there is no edge here since we assume that the derangement graph is a complete multipartite graph. So there is no edge here. So they are in this part, in fact, the part that contains the identity. And we can also prove that a point stabilizer, in fact, is in this part. So we can characterize these groups in the following way. So this f of G is the subgroup of G that is generated by the permutations with at least a fixed point. And in this case, it is very special because this subgroup is equal to the union of these point stabilizers. So this is why we do not have the EKR property, since as long as f of G is not a trivial subgroup of G, then we will always have an intersecting family that is larger than a point stabilizer. So this is what we did, and so we were looking at complete multipartite derangement graphs, and we looked at the library of transitive groups in GAP and SAGE. So we could find complete multipartite derangement graphs. So k-partite graphs here, where k is in this set, and the degree of the group here is at most 37. I think that's what we have in GAP. So what we noticed is the following. So there are only 4 groups with whose derangement graphs are complete tripartite graphs, and we couldn't find any transitive groups whose derangement graphs are complete bipartite graphs. The only one that we found is the one that corresponds to the group SIM2. So we have the identity and the permutation, the transposition 1, 2, and this is the only thing that we could find that was bipartite. And so this is exactly what we proved with Pablo Spiga and Karen Marr. So if G is a transitive group, a finite transitive group, so the derangement graph of G is bipartite if and only if the degree of the group is at most 2. So the example that I showed earlier is the only example. And We also showed something that is much stronger, in fact. So when the degree of the group is at least 3, then gamma of G has a triangle. And to finish this talk, let's talk about some open problems for intersection density of groups. So here we let G again be a finite transitive group. So it is possible to prove that when the degree of the group is a prime power, then the intersection density is equal to 1. So we have the Ikea property. And when the degree of the group is 2 times an odd prime, then rho of G is a rational number between 1 and 2. And recently, it was proved by Marusic and his colleagues that in this case, what we only have, in fact, is just rho of G is either 1 or 2. And to finish this talk, so the conjecture that I have is that when P and Q are distinct odd primes, then any group, any transitive group of degree PQ has intersection density equal to 1. And so that is all I have today. Thank you for your attention.
All right, let's thank Biddy for a fantastic talk. Does anyone have any questions for Biddy? I guess I have a question. I'm wondering, do you think you'll use like derangement graphs as well to look at your conjecture?
Yeah, I think we'll have to use the derangement graph, but I think the only method that we have to prove this right now is to use the classification of finite simple groups. So it might be a bit difficult.
Yeah, thanks. All right, let's think. Oh, sorry.
Sorry, I guess I also have a question. I'm curious what evidence you have for your conjecture. Like, what made you convinced this was true?
Well, so we used gap first of all, and so when you look at the circle of these groups, so I think I can prove that when the circle of some of these, well, so when we take G to be a primitive group first of all, and the circle of the group is the alternating group, then I think I can prove that the intersection density is 1. And in some cases, when the circle of the group is also like PSL2 of Q, I think it works as well. So I think there is like three other infinite families of groups that I need to consider, but they are difficult, I think, and I don't understand them that much yet.
That makes sense. Thank you.
Yeah.
All right, let's thank our speaker again.